Chapter 3.3, Truth Tables for Negation, Conjunction, and Disjunction. By determining when statements involving negation, conjunction, and disjunction are true, and when they are false, will enable you to draw conclusions. Classifying a statement as true or false is called assigning a truth value to the statement. The negation of a true statement is false, and the negation of a false statement is true. This can be shown in table form and is called the truth table for negation. Notice that not P has the opposite truth value from P, so this table shows every possible case. If P is true, not P must be false. If P is false, not P must be true. For a compound statement, however, there are 4 possible cases. Both statements may be true. The first statement true and the second one false. The first statement false and the second one true, or both false. Okay, so this is a part of a truth table for a conjunction, an and. Notice it's only true when both statements are true because of what it means to be and. Right? This one has to be true, and this one also has to be true for the entire statement to be true. Here's a representation of a truth table or part of a truth table for a disjunction or. Notice a disjunction is false only when both simple statements are false because of what it means to be or, meaning this can be true or that can be true, or they can both be true to make the entire statement true. Okay, truth tables can be used to gain a better understanding of English statements. Breaking compound statements into simple statements will enable you to construct truth tables. So first, turn the compound statement into a symbolic statement if necessary. Never begin with a negated statement, however. For example, if your statement was, I do not have a dog and I live in Weatherford, your statements are going to be P, I have a dog, and Q, I live in Weatherford. Then you'll use the negation inside your table. List all possible combinations of truth values. Okay, so you're going to make a table with 4 rows if you have 2 simple statements, 8 rows if you have 3 simple statements, 16 rows for 4 simple statements, etc., plus a row for your heading. In other words, you can determine the number of rows just like we did the number of subsets 2 to the n, where in this case n is the number of simple statements you have. Okay, next determine each column heading. The first columns will be for your simple statements. It might be a good idea to do negations next. Afterwards follow the dominance of connectives, including parentheses. And the final column heading should be the entire given compound statement. So use each column heading and then use each column heading to fill in the truth values. Alright, so let's try this out. Let's try to construct a truth table for this statement. First thing I have to do is turn it into a symbolic statement, which this one already is, so my first step has been done for me. List all the possible combinations of truth values. In other words, because I have a P, Q, and an R, right? That's 3 simple statements. I'm going to need a table with 8 rows, including my heading. So, alright, so here's my heading column. Let's do my heading. And then I'm going to do 1, 2, it's going to look like a flag instead of a table, 3, 4, 3.5, 4, 5, 6, 7, 8. Alright, now I'm going to have a column for P, Q, and R. And then I've got to do every possible combination of truth values. An easy way to make sure that we have every possible combination covered is, first of all, to do half of your first column true and half false. So I'm going to have 4 trues and 4 falses. Okay, and then for my next column, I'm going to just look at the trues, and I'm going to do half of those true and half false. And the same for the falses. Half of them true and half false. And I'm going to continue in this manner, no matter how many statements I have, columns for statements, and my last column should coincide to a column that goes true, false, true, false, true, false. Let's see if that's true. If I take half of my trues and do them true and half false, yeah, a true, false. Half of this true and half false, yes, true, false, true, false. That's the way I organize my table every single time with 3 simple statements. My table will always look like this in the beginning. Now, my next column, it's a good idea to do your negations unless your negation is outside of parentheses, okay? Because I'm going to go across by my dominance of connectives, my least dominant, so I'm going to do not Q's. Well, this column I'm going to fill in based on not Q. So the only one I'm considering is my column of Q's. That's all I'm considering right here. So if Q is true, not Q is false. If Q is true, not Q is false. But when Q is false, not Q is true, not Q is true, only looking at the Q column. So not Q would be false in this situation, false, true, true. A negation must have the opposite truth value as the original statement. Okay, next I'm going to do inside parentheses. So this is not Q or R. Okay, and I'm only looking at the not Q and the R column. That's the only 2 involved in this piece of my statement. And now or means as long as one of them is true, one or the other or both, the entire statement is true. So one of them is true here. The only time an or is false is when both are false. They can both be true, or either one can be true, but if they're both false, the entire statement is false. Your last column should look exactly like your statement that you're devising the table for. Okay, now in this case, let me change to red just so I can say I'm comparing the P column with this column. And I'm basing it on what and means. P and this. So in order for an and to be true, both have to be true. Right? So in this case, P and this is true. But here they're not both true, so the entire statement is false. Here they are both true. Here they are both true. They're not both true here. Not both true here. And not both true on either of these. So that means this is your truth table. And right here, this is the column that tells you the truth value of this statement. So in other words, this statement is only true under the conditions when all 3 individual simple statements are true. It could still be true, however, if Q is not true, or it's even true when Q and R are not true. So it's very important to be able to determine the truth value of statements. We get statements thrown at us all the time. And again, right here, this one shows that I could really create a sentence where two of the three things I'm saying in the sentence are not true, but the entire value winds up being true. So if I get called on it, or it gets, or someone's trying to prove it, they have to determine it is true. But two of the three simple statements involved are not true. A compound statement that is always true is called a tautology. Okay, a tautology. Think about the logic in the following statement. From a commercial for a high-fiber cereal. Okay. Some studies suggest a high-fiber, low-fat diet may reduce the risk of some kinds of cancer. From a strictly logical point of view, may reduce means it may reduce the risk of cancer or it may not. The symbolic translation of this sentence is a tautology. The claim made in the cereal commercial can be made about any substance that is not known to actually cause cancer, and then it will always be true. Okay, so here we have a truth table that shows the truth values of a compound statement for every possible case. However, you can also determine the truth value for a specific case in which the truth values of the simple statements are known. This does not require constructing an entire truth table. Simply construct one row. For example, to determine the truth value of the statement, I do not teach English and I own a Mastiff. Your first thought is to turn it into a symbolic statement. So P, I teach English. Q, I own an English Mastiff. All right, so if I'm going to turn that into a symbolic statement, I do not teach English and I own an English Mastiff. So if I'm constructing a truth table, I only have two statements. So I have P and Q. I'm not doing the entire table because I know that P is false and Q is true. So to determine the truth value of this entire thing, I already know which row of the table coincides to these simple statements. So not P has the opposite truth value of P, so I'd have a T. So on not P and Q, I'm only comparing these two statements based on and. For an and statement to be true, both of these simple statements that I'm considering have to be true, and they both are. So that is a true statement. All right, let's see if we can work some word problems. Construct a truth table for the given statements. All right, P and Q. It only has two simple statements. So I know I need 4 columns, plus my header, right? So I'm going to have my header plus 1, 2, 3, 4. First thing we're going to do is make a column for each simple statement. In this case, P and Q. Yes, that's a Q. Okay, so I'm going to make half of these true and half of them false. And then half of my trues are going to be true and half false. Half of my false is true. Double check for me is that this last column better go true, false, true, false. Every truth table with 2 statements looks like this in the beginning. Now, starting with my least dominant, I'm going to do not P. Okay, I'm only considering the column P. And I'm just going to change the truth value because not P has to have the opposite truth value as P. So I'd have a false, a true, a true. Now, inside parentheses is the next thing, so I have not P or Q. Okay, I'm looking at not P and Q based on or. Or means as long as one of them's true, the statement's true. When they're both false, the statement is false. And then my final column should look just like my final statement, or my total statement, or and again, just for emphasis so we can keep track of what we're doing, I'm looking at this column only, and I'm negating it, right? So I got to have the opposite truth value of what's in this column. So false, true, false, false. Okay, over here, I still have only two statements. Look, one's a P and one's a not P. That's still P. All I have are P's and Q's. So again, 4 columns, plus my header. So header. 1, 2, 3, 4. Now, these first 2 columns will look exactly like that. Every truth table with only 2 simple statements will look exactly the same in the beginning. So half of them true and half of them false. And then half of these true and half of these true. All right, I've got a negation, so I'm going to do not P. Just going to do the opposite truth value of P. So I'll have false, false, true, true. Okay, my parentheses are telling me that P and Q is my next determination. So I'm looking at the P column and the Q column only based on what it means to be and. In order for an and statement to be true, both simple statements have to be true. Okay, they're not both true, not both true, not both true. And then the only thing left to judge, the only connector left that I haven't used is this or. So my final column should look exactly like my original or my total statement, and I'm going to be comparing this and this column based on what it means to be or. For an or, as long as one of them's true, the entire statement's true. The only way it's false is if both statements are false. And there's my truth value. All right, so for this one, how many rows does my table have? Right, it's only P's and Q's. So it's going to look just like the previous 2. 4 rows. And a header row. 1, 2, 3, 4. P, Q. My only simple statements. So 2 true, true, 2 false, and then true, false, true, false. Okay, I've got a not Q. So I'm going to write the opposite of everything that's in the Q column. So false, true, false, true. I also have a not P. So I'm going to write everything the opposite that's in the P column. False, false, true, true. Okay, I have parentheses here. I have a P and not Q. So I'm looking at the P and the not Q based on what it means to be and. Remember, with an and, they both have to be true to be true. Okay, then I've got inside my other parentheses not P and Q. So I'm going to do not P and Q based on what it means to be and. They both have to be true, so they're not both true, they're not both true, they are, and they're not. Not both true, not both true, they are, and they're not. And then my final column needs to look like my actual statement. I don't really have room to write that here, so I'm just going to say that goes in there, and I'm going to base that off of this column and this column based on what it means to be or. So remember, with an or, as long as one of them's true, the entire thing is true. So one of these is true, one of these is true, and neither of them are true. So what about the next one? How many rows do you think I'm going to have for it, not counting the header column? This time I have an R, a P, and a Q, so I have 3 simple statements. So my table is going to need 8 rows plus a header column. So let's do a header. 1, 2, 3, 4. Wow, that was good. 5, 6, 7, 8. And my simple statements are PQR, so I'm going to have a P, a Q, and an R column. P, Q, R. Half of my P's will be true, and half of them false. Okay, so half of these trues need to be true now, and half false. Same thing for the false. Half of them true, and half of them false. Okay, now half of these trues true, and half false, which gets me to perfect. True, false, true, false, true, false. It's kind of a check for me. If my last column following that method doesn't wind up true, false, true, false, true, false, I've made a mistake. All right, I've got a not P. So I got to write the opposite truth value of P. So 4 falses and 4 trues. And I've got a not Q. So I've got to write the opposite truth values for the Q's. So false, false, true, true, false, false, true, true. I've done my negations. The next thing is inside the parentheses, so I have R and not P. And I'm going to make that determination based on, of course, R and not P, based on what it means to be and. For an and statement to be true, both have to be true. So this is false, 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 true. They're both true right here. false, true again, and false. Now my last column should encompass my entire statement. And I'm looking at this column and judging it with not Q, based on or. As long as one of them's true, the entire statement's true. Both false, both false. Oh, one is true, one is true, one is true, both false, one is true, one is true. Okay, let's construct a truth table for this statement. It is not true that I ordered pizza while watching late night TV and did not gain weight. Okay, so it is not true. I don't want to include that. So I want it to say I ordered pizza is P. I ordered pizza while watching TV. I'm going to shorten it and just say I ordered pizza and did not gain weight. Q, I did not gain weight. I only have two simple statements. Right? So, how big's your table going to be? Yeah, 4 plus a header. 1, 2, 3, 4. P, Q. Half true, half false. True, false, true, false. Okay, first of all, I've got to change this into symbolic form. So it is not true that I ordered pizza and did not gain weight. Oh, look what I did. I did not gain. I did gain weight. But my symbolic form says, it is not true that, okay, it is not true that I ordered pizza and did not gain weight. Okay, remember, it is not true that. That means I've got this out front instead of, it's not just that I did not order pizza, right? It's not true that I ordered pizza while watching late night TV and did not gain weight. So here's my symbolic statement. So I want to do not Q first, which is going to have the opposite truth value of Q. So false, true, false, true. Then inside the parentheses, P or not Q. So here's P, here's not Q, or as long as one of them is true, the whole thing can be true. And then my final column is my entire statement. It is not true that I ordered pizza while watching late night TV. Oh, I've really messed this up again because I'm doing an or over here and it says and. So, sorry guys. Let me go back and erase this for us and make it an or. Alright, and then we'll refresh this and say what's going on. Sorry. I looked up here and I also saw that out of the corner of my eye. Alright. If you ever see me make mistakes, I'm really good at that. In case you haven't noticed yet, be sure and contact me if you have a question about something you see. Maybe like on this one, if I had not caught that and I left it up as the or and you're confused, be sure and contact me and make me look at that and clarify any issues. Okay. All right. So it is not true that I ordered pizza while watching late night TV and did not gain weight. So that doesn't change my setup of the table or the not Q. But here I want to do P and not Q. So when I'm looking at these two columns based on and, the only way that can be true is if they're both true. So that will definitely change this column. Okay, they're only true, both true in one instance. When they're both true, of course. Okay, so now I have not true that. P and not Q. Okay, my entire statement. And all I have to do is negate on this one, this last column right here. So true, false, true, true. On this last one, notice how it doesn't say construct a truth table. It just says determine the truth value for this statement. And in order to determine the truth value, I have to know when P is true or false and Q is true. So basically what that means is, oh, I'm just making one row, including your header row, of the table. The one row when P is false and Q is true. Right? So pay attention to that. Is it asking you to make a truth table? Or is it asking you for the truth value when the particulars are known about your statement? So if P is false and Q is true, it's like just asking me to make that one row, right? Instead of the whole table. All right, except I'm going to do it for this symbolic statement. So first of all, I'm going to do not P. The opposite of P, since in this case P is false, is true. Then I'm going to do P or Q inside the parentheses. I'm going to look at the P and Q column based on what it means to be or. As long as one of them's true, the whole thing's true. And now I'm going to do P or Q and not P. So I'm looking at P or Q and not P based on and. Well, for and, they both have to be true, and they are both true. So now I know that this is a true statement under these conditions. Alrighty. Go have fun now doing these on your own. I'll see you next time.